of this agricultural production, you can understand why this is a water resources management problem that has a relevant social implication. Because if the economics of the Parmesan, the economy of the Parmesan cheese is impacted, this is really a big problem in terms of occupation of the population, in terms of economical support to this wide area. I mentioned to you land reclamation. Land reclamation, which means the drying up of marshes, was organized starting from the Middle Age, starting from about 500 years ago, was organized in consortiums, because land reclamation continuously need to be carried out and continuously need maintenance. It's not just needed that you dig a channel, it's also needed that you keep this channel efficient, meaning that somebody must take care of channels if you want to dry up a region. Very often these channels, as I mentioned to you, are also used for irrigation, and therefore if you want irrigation to be efficient, you need people taking care of the channels. So people organized in consortiums, meaning that people living, typically farmers, 500 years ago in a given area, got together and decided to set up a consortium. They paid for it in order to take care of channels and hydraulic works. So they agreed to put some money, each individual living in the country, in the region, and to set up an enterprise, the consortium, that organized itself to take care of the channels. So this is how Consorzi di Bonifica, Reclamation Consortium, were born. And this is the reason why everybody living there is asking to pay taxes on reclamation. Some people don't understand why should I pay taxes for reclamation. The reason is that you don't understand that in the past people committed to pay for the reclamation activity. And people don't understand that if you stop the reclamation activity, you would have very relevant consequences on the economy of the region and therefore on ourselves. So in this province of Reggio Emilia, historically there were two consortia for irrigation which were joined about 3 years ago in order to reorganize the state administration. They asked the consortium to merge, but still they are working. And about water quality, these are the river cross sections that were identified in reply to the call of the European Union to specify what are the significant rivers. And therefore, through subsequent laws for this province, were identified a series of cross-river sections along the main rivers. So you see a section along the Po River, which is located in the province of Reggio Emilia, two sections along the Secchia River, one in upstream and one downstream, one section on the coastal river, one section on a minor river, Canalazzo Tassone, which is very important, by the way, because it's the outflow of the water sanitation plant Depuratore of Reggio Emilia, and also another section along the Crostolo, and two sections on the Secchia River. The Tresinaro is just inflowing into the Secchia River. And you see from this picture that was derived at the beginning of this activity, therefore was derived soon after the year 2000. With the red you see a very critical situation, with the orange you see critical situation, with yellow a sufficient situation. Sufficient means already meeting the EU requirement, but just on time, just above below threshold. and green means buono, means okay, that's good. So you can see that for the province of Reggio Emilia there are some very critical situations which are typically located downstream that needs to be resolved. So, how can the situation be resolved? Of course, as I said, one first requirement is to release the environmental flow. And in order to determine the amount of the environmental flow, you first of all have to determine how much water is flowing along the river, which I said is one very relevant problem for us. Measure water in absence of historical measurements and very often without the possibility to set up measuring equipments because of economical restrictions. So first of all, one has to quantify water flowing into the river. And if you cannot take advantage from measurement, as I said, there are some hydrological procedure that allows you to make an estimation. And we will go into details in this course, how to estimate water availability. And after applying an hydrological simulation procedure, so I'm talking about the third option that I mentioned to you yesterday, generation of synthetic data. I told you about three options: data, using observed data, rainfall runoff model, and generation of synthetic data. In this case, the Emilia-Romagna region developed a very interesting study, which is described on the Water Resources Management Plan, to simulate synthetic data for all the rivers, relevant rivers of the region. And as a result, they were able to quantify mean monthly river flows along the relevant rivers. Again, mean monthly river flows. Let me give you some more detail because we are entering now in some technical issue. River flow, we already defined what is. You take a river cross-section, the river flow is the volume of water that is passing through the section in unit time. It is usually expressed, the unit of measure is volume over time. Typically is cubic meters per second. Cubic meters per second. But in some cases, it's also expressed in liters per second. Make sure that you well remember that 1 cubic meter is 1,000 liters. This is very much important for a water resources manager. If you go and speak with one person and this person realizes that you don't remember how many liters are in a cubic meter, you are lost. Okay? This is very much important to remember. And I tell you that sometimes I still have to think about 1,000, yes, 1,000. And it's very important. Because every farmer knows more or less how many liters are contained in a cubic meter of water. Now, this is river flow then, and I mentioned that in this case, the region, the Emilia-Romagna region, decided to estimate mean means long time average, mean monthly river flows. Mean means long time average, monthly means long time average over a given month. And river flow was quantified at the monthly scale because it was deemed to be sufficient for studying optimal irrigation strategies and environmental flow requirements. The question would be, why don't you quantify the flows at daily time scale? It would be more precise. And even hourly time scale would be more precise. The problem is that as you reduce the time scale, modeling becomes more complicated. This is also quite understandable. If you want to estimate a variable at a monthly time scale, the level of detail that you have to consider in your estimation model is lower with respect to estimating the same variable at daily time scale, because at daily time scale you have to take into account sub-monthly variability. And if you want to go to the hourly time scale, you have to consider sub-daily variability. So you increase the level of detail of your representation, and therefore it's quite intuitive that you have to increase the level of detail of your model. So there is on the side, okay, let's refer to the monthly time scale. Is enough. Why it's enough? Let's try to better understand. It's enough because we are talking of lower flows here. We are talking about low flows. Low flows typically are not much varying in time. Definitely they are less varying than high flows. Because you see when floods occur, you see that the flood, even on the Po River, gets resolved in 1 week, which means that in 1 week you have a very significant variation of river flow from a dangerous level to a normal level. Instead, if you look at the river during low flows, from one day to another, you don't see big changes. Because of course, low flows are slowly varying. And therefore you can make reference to this time scale. But you will see that in hydrology, the issue of time scale is extremely important. So we have to decide what kind of variability do we need to study. In this case, monthly time scale was enough. We will consider this detail during the course, but I want to anticipate what the problems are. So, the reason quantify these flows, I'm not entering into the detail of the simulation procedure because I will do so later. But in a way, they were able to generate synthetic series. Now, second step, quantify the water demands. So on one hand, you have to quantify water resources availability. The second step is to quantify water demands. Why? Because I anticipate to you a basic principle of water resources management. As I said, the theory underlying water resources management is not very structured, but nevertheless there are some basic principles. And if I was asked to identify the real basic principle of water resources management, I would say water balance. In any water resources management problem, we have to draw a water balance. I have to estimate how much water I have available. I have to estimate the water demands and compare them. If I have enough water, I don't have the problem. So it's very likely, if people called me to solve a problem, that I will find that demands are higher than availability. At least in some parts of the year, in some months. Therefore, as I said, the first step is to estimate water resources availability. Second step is water demand. What does it mean, water demands? In this case, water demands consist in estimating the water demands consists in estimating water requirements for civil, industrial, and agricultural use. In this case, it was done for the province, and the picture is here. You see that civil use is about 20% of the total demand, is about 64 millions of cubic meters per year. Then we have industrial use. It's about, the red one, 28%, sorry, it's 9%, 28 millions, while the agricultural use is 71% of the total water withdrawal. These are, in particular, sorry for the Italian, water withdrawal at the source. Some more detail. Why I say at the source? Because the water that you take from the river is higher than the water that you deliver because of water losses. So when you say water consumption, you have always to say at the customer or at the source. For irrigation, I always say water consumption at the field or at the source. The difference is just water losses, which for irrigation are about 50% and for civil use are about 40%. So it's an important portion of the withdrawal at the source that is lost for losses. Again, what can we see from this picture? We see a picture that is more or less the same worldwide. Namely, water for food, water for irrigation is the main reason for water consumption. And you see that here the relationship is 3 times, more than 3 times. In many countries, underdeveloped countries, you will see that the proportion is even more in favor of irrigation, like 1 to 10. But even in this case of a very developed area, where agriculture is important, but not really the only one means of sustainment, even in this case, you have water for irrigation, which is 3 times higher, which is 2 times higher than the sum, more than 2 times higher than the sum of water for civil and industrial use. This means that water for food is the main concern for a water resources manager. Therefore, when we are talking about optimization of water resources, optimization of water savings, we must know that agriculture is the main reason of concern. Water for civil use, of course, it's important to save water for civil use, but it's not so important as saving water for agriculture. This is very important to keep in mind. And let's look at some other figure, like if we make reference to the civil use, how much water is taken from groundwater and how much water is taken from surface water. You will see the proportion here. Groundwater is about 86%, surface water is about 14%. And this is a common picture all over the world. For civil use, much of the water is taken from groundwater. The reason is that, of course, it's more expensive, but we are talking about volumes, water volumes, that are less significant with respect to agriculture. And therefore, we can afford the expense of a well. I'm not sure the pronunciation is correct, it's a pozzo, I hope you understand. It's the hole in the ground from which we take water, which is probably less expensive than digging a channel or placing a pipe to bring water from the river to the sea. It's probably more convenient to dig the well instead of bringing a pipe or etc. And also there is to say that groundwater from a quality point of view is better, usually, and is safer than surface water. Now let's look at industrial use. You see that, again, much is taken from groundwater directly, and a limited portion from aqueducts, water supply system, civil water, and from surface water. Now let's look at agriculture. The picture is a bit different. We have surface water, which is playing the part of the lion. It's a major part of water for irrigation is taken from surface water, and in particular 63% of the water that is used for irrigation in this province of Reggio Emilia is taken from the Po River, which is water that is not very high quality, but for irrigation is fine. At least we assume that it's fine. And then we have surface water from the Apennines, which is high quality water, which is 20%, and then groundwater, 17%. So you see that the proportion is reverted. Surface water is more important. Even if we should consider that in this case, the water from the Po River must be pumped up in order to be able to use it for irrigation. So it's costly in any case. Okay, now let me go into the details of the case study. So what's the problem here? The problem is that for this river, the Enfa River, which provides water for irrigation in the area that produces the Parmesan cheese, during summer we don't have enough water to give to farmers. And they can't take water from the Po River because it's too far, and therefore they take water from groundwater. But they are unhappy because they have to pay a lot to pump it. This is the historical problem. So starting from about 150 years ago, people started wondering what solution could they find for solving this problem. Basically, channels for irrigation during summer ran out of water. The first issue was to estimate water resources availability, and the issue was solved by the region, by the Emilia-Romagna region with the simulation procedure. But nevertheless, there were some complaints by farmers, because when you talk about water and you make assessments about water, you always have people complaining, of course, because if you find that there is more water than they expect, they complain. And the same for the opposite. If you find that there is less water than they think, they in any case complain. Because in any case there is an impact on their activity. So in this case it was necessary to convince stakeholders, farmers and administrations to make a comparison between the quantities of water estimated by the region and the measurement that were taken by the consortium on river flows. The measurements were spotty, not continuous, but in any case a comparison was possible. And this comparison gave satisfactory results, proving that the simulation procedure that was set up by the region was reliable. You may wonder why, if we had data, we made the simulation, because data were spotty, as I said. So for some months of the year, we didn't have any data. Of course, in order to compare the results, we could limit the comparison to the periods for which data were available. But if we want to really manage the problem, to really find an optimal solution, we have to rely on a very consistent database. So the simulation was indeed necessary. Then we had to simulate with a mathematical model how the system works, based on water availability and basing on water demands that were estimated with a very refined analysis that took into account the type of agricultural production, the displacement of any field, if it was very close to a well or not, if it was close to a channel, close to the river or not, because any of these details is influential on the farmer's decision whether to irrigate with groundwater or surface water. So a refined analysis was made to estimate necessities, water demands, and their location. But also, based on this data, you have to make a comparison, which is as more detailed as possible, between availability and requests, in order to understand how the system works. Because first of all, you have to well understand how the system works through a water balance. You have to understand if the farmers irrigate with groundwater or surface water, what are the reasons for irrigating with groundwater or for surface water, because knowledge of the problem allows you to make assumptions on possible solutions. allows you to speak with the farmer and say, what if you turn your irrigation system from using groundwater to surface water? What would be your expectation? And if you want to be able to speak with farmers, you have to know everything about their decisions, everything about the dynamics of the system. And therefore, a simulation model was built. And let me describe it, because I think it's interesting. First of all, water demand at the field was estimated, as I mentioned to you, and was computed depending on crop spatial distribution. Crop means type of cultivation. And was estimated depending on water requirements of each crop, and coefficients were introduced to account for different climates. Because even if you are working in the same region, you have areas that are warmer than others, and therefore you have to correct the water demands of each crop based on climates. And permeability of the soil is very much important. If you have a very permeable soil, you need to provide to crops more water. And therefore permeability was studied in detail, and coefficients were introduced to take into account it. And then water availability, because if you have a lot of water, you use more water with respect to a farmer that is pushed to save water. What we see is that farmers, for the same crop and same requirements, use more water in May than in July, because in July they are pushed to save water. Therefore, for identical condition, you need more water in May with respect to July, and you have to take this into account. And then, irrigation technique. This is very much important, because there are many different irrigation techniques which are characterized by different water requirements. And let me make an example. There is the convincement in this region that irrigation should be flood irrigation here. Flood irrigation means that you release the water on the ground and you allow the water to flow on the ground downstream until the lower part of the field is reached by the water. This is called flood irrigation. In Italian it is called irrigazione per scorrimento. And in this way, which is a traditional way of irrigating, because you don't need instruments, you just need a small channel bringing water, and you allow the water to flow over the field. In this way, however, a lot of water is consumed. For what reason? Because of course you have to make sure that water arrives at the end of the field. In order to be sure that water arrives at the lower part of the field, you have to make sure that water flows out of the field. You cannot calibrate the irrigation system just to reach the lowest point. You have to calibrate irrigation in order to make sure that everything is wet and therefore a lot of water is lost. This kind of historical irrigation is deemed to be the only one possible for this type of fields. Why this? Because first of all, it's a tradition. And second, what would be the alternative? The alternative would be to use sprinklers to mimic rainfall. And in Italian it's aspersione, meaning using this kind of devices that rotate and spread the water by mimicking rainfall. In this case, you need a more complex system, because you need pipes, not just a small channel. You need pipes, you need pressure pipes to bring water to these sprinklers. So you need to spend some money to set up the irrigation system, but the result is that you get the fields, you get wet the fields, because if you mimic irrigation, you have water that is falling from above, therefore wettening the leaves and the fields. And there is the convincement by farmers that in this, by using this technique, when the weather is sunny, you practically burn the crops. You know that people say that you don't have to wet your vegetable garden during summer because, or you don't have to make the leaves of like tomatoes wet, because with the sun the effect is burning of the leaves. So farmers are convinced that you can't use this irrigation system because it burns the crop. Okay, therefore you have to take irrigation technique into account. By the way, experiments were made by using sprinkler irrigation, and no changes were observed in the production, in the crop production. In this case, we are talking about a crop that is called stable fields. It's just grass that used to feed the cows for producing the milk to produce the Parmesan cheese. So they didn't notice any change in the production. Therefore, farmers adopted a new theory. They started to claim that the quality of the milk and the quality of the cheese is in any case impacted by changing the irrigation system. Because you know, the Parmesan cheese is unique, and we don't know what is the reason for the uniqueness. We still don't know why. It is produced all over the world, only in the province of Reggio Emilia, along the Enza River. But we don't know what is the reason for the uniqueness. So of course people think that the reason could be something that we don't understand, and something related to irrigation. So they claim that probably by changing the irrigation system we may lose quality of the Parmesan cheese. So they set up a team of persons that were asked to taste the cheese that was produced with the two different irrigation systems, and they didn't find any difference in the quality of the cheese. This is a lot of fun to tell you, but I want to really you to understand that what is indeed the problems with water resources management. Sometimes the problem is very complicated, and it's also a communication problem. So water demand at the field was estimated, and then leakage, water losses must be estimated, because once that you know the water demand at the field, you have to translate the water demand in water requirements from the river at the source. And therefore you need to estimate leakage, and therefore you can get an estimate of the water demand at the river. And then you are able to compare for each day, not any single month, as I said before. We decided to go to the daily detail. So for each single day, in a 10-year period, in order to get an estimate of the long-term average, we compare the water demands with water availability. At the end, we were able to estimate the water deficit. So the amount of water that we would need to take from the river to completely satisfy water demands. And then again, by taking leakage into account, we were able to estimate the water deficit at the field. And finally, you get an estimate of this water deficit, which is really very important, because people claim that they don't have enough water, but we don't know how much water is needed to compensate their needs. And you see the result was that for the Enza River we would need about 60 millions of more water during the summer period. 60 millions of cubic meters. Once that you know the water request, you can finally propose solutions. But you have to estimate the water deficit, because the solution is very much varying. You have several options available. For instance, one option, I will tell you later, is to build a dam along this river. And of course, to build a dam is a very impacting option from an environmental point of view. Therefore, you should consider also other alternatives. But of course, the suitability of an alternative depends on the amount of water that you have to find. And here we found that for the Secchia River it's not a big problem. For the Enza River, indeed, it's a problem. But keep into account that this is a water deficit at the field. Okay. Strategies then. A first option was proposed by taking into account that along the Enza River a lot of mining activity is planned and was done in the past. Mining activity means that you take gravel from the riverbed or from the lands that are displaced very close to the river, and the gravel is typically used for building roads, for building buildings, etc., for making the concrete, or for building activities in general. And typically, when you finish a mining activity, you have an hole as a result that you have to fill in some ways. And in the past, they used to feed the hole with the lime, with some resulting material from the gravel activity, from the mining activity, sorry. And they used to restore it by bringing it back to the agricultural use or other restoration option. And now they are considering to use these holes to store water. To store water during winter, to be used during summer. Of course, we need a lot of water here. We are talking about, as you have seen, 60 millions of cubic meters. But a first option is let's at least compensate the environmental flow requirements. So we have a problem in the problem, because we have an historical problem, but we also have the environmental flow requirements to grant. And the amount of water needed for the environmental flow is about 6-8 millions of cubic meters of water during the summer period for the Enza River. And 6-8 millions of cubic meters is not that big amount. These lakes can easily contain a couple of millions each of cubic meters. Typically, the volume of a mining activity can reach about a couple of millions of cubic meters. So with 3-4 lakes,